Welcome to Shanti Peace for Mathematics. In my previous videos, we have talked about a Rolle's mean value theorem that I have written as RMBT and Lagrange mean value theorem that in short it says LMBT, which states that the RMBT states that f is a function which satisfies the three conditions. F is continuous on a closed interval AB, differentiable on open interval AB, and the third condition is f of A is equal to f of B, then there exists at least one C such that f dash of C is equal to 0. Geometrically, if you can see that, then if you have a graph of the function which is continuous and it is a smooth, or I can say at every point there will be exactly one tangent. The third condition says that the y coordinates of the any two points will be the same. In between that interval, there exists at least one C on which the tangent is parallel to x-axis. The generalization of RMBT is the LMBT. By dropping out the third condition, if you drop this condition from RMBT, we obtain the LMBT. That means f is continuous function and f is differentiable, and there exists at least one C such that f dash of C is equal to f of B minus f of A upon B minus A. Now the Cauchy's mean value theorem that we are going to discuss in this lecture, which is actually a generalization of LMBT for two functions. So for that, let's say the given two functions f and g, both of them are functions which are defined from AB to R. And if you consider this f is continuously differentiable function and g is also continuously differentiable function, then for f you will have there exists at least one C such that AB such that f dash of C is equal to f of B minus f of A upon B minus A. And for G also you have another point D which is in between AB interval such that f dash of D equal to G of B minus G of A upon B minus A. Here it is G. So the question is what we can do if I take a reciprocal of this two. So on this side it will convert to f of B minus f of A upon G of B minus G of A. But here the C and D are the different points. So the question is, can we have a same C for both this function? That means f dash of C upon G dash of C, is it we have or not? That is exactly the Cauchy's mean value theorem is. Here if you apply the Lagrange mean value theorem separately to both the function, we have for some function we have the C and for the G function we have a D. But the question is, can we have the same point here? And that is exactly the Cauchy's mean value theorem, which is a generalization of Lagrange mean value theorem for two functions. So how this Cauchy's mean value theorem states? The Cauchy's mean value theorem states like this: f and g, both of them are functions which satisfies these three conditions. The first one is f and g, both of them are continuous on a closed interval AB. F and g are differentiable on open interval AB. And the third condition is the derivative of g dash of x is non-zero for every x is in AB. That is the third condition is required. Then there exists at least one C, it is in between AB, such that f dash of C upon G dash of C equal to f of B minus f of A upon B minus A. This is the things we got. Now here the first question is arise why this condition is given to us and why we can divide this quantity. This quantity we can divide only if it is non-zero, otherwise it does not exist. And the second question is arise why this condition is given to us. So first let us assume that, let us say this G and f of B and f of A is same. So let us assume, so we will start with the proof. if g of b is same as g of a, then what we can say? We note that g is continuous on closed interval AB and g is differentiable on open interval AB by our hypothesis. The hypothesis says that g is continuous and g is differentiable, and this thing is there. So that means g satisfies all the condition of Rolle's theorem. So therefore there exists at least one c in the interval AB such that g dash of c is equal to 0. But this is not possible, which is contradict to the hypothesis 3. The hypothesis 3 says that the g dash of x is non-zero. So now we understand that why this condition is given here. Okay, so what we can write, which is contradict to hypothesis 3. So that means we have given this condition is that. Now let us do some rough work and try to prove this thing. And obviously we are applying the Rolle's theorem to prove this statement. So as we have did in the Lagrange mean value theorem, how we have proved, we have defined some function, and on that function we have applied the Rolle's mean value theorem. Here is also we are doing the same thing. So what I'm doing, I'm just doing some calculation here. So this is my rough work that I'm doing. What I have to prove? I have to prove that f dash of c upon g dash of c is equal to f of b minus f of a upon g of b minus g of a. This is my objective, is to prove. And this quantity is a constant quantity. So I'll say it is capital A. Instead of c, we'll write fx upon g dash of x. So this expression is this, f dash of x minus a into g dash of x equal to 0. So ultimately, if I want to apply a Rolle's mean value theorem, that means I need some derivative is equal to 0. So instead of x, if it is c is there, then we have f dash of c minus a g dash of c is equal to 0. So now we need to construct the function whose derivative is this, and that we can obtain by integrating this expression. So if I integrate both sides, we'll have fx minus a into gx equal to 0. So this is my function that I will start with, and I will apply the Rolle's mean value theorem onto this function, and we determine this value of a in such a way that it will satisfy, suppose this function is phi, then it will satisfy phi of b equal to phi of a. So let us try to do this. So let us define the function phi from AB to R as phi of x is equal to f of x plus a g of x. See, in the previously this a is that it is minus, but this is a constant quantity we have assumed. So instead of a, if I take minus, then we'll have a plus. So no problem if I take it is minus or plus sign. It does not make any differences. So ultimately we have this where a is a constant to be determined such that phi of a equal to phi of b. So we have to determine this value of a if this condition is satisfied. Now what is phi of a? As per the definition, it is fa plus a into g of a. and phi of b is fb plus a into g of b. So if you simplify that and you can solve for a, you will have it is a into, if I take this value on the other side, then it is g of b minus g of a, and on the other side you will have f of a minus f of b. So therefore you will have a equal to minus of f of b minus f of a upon g of b minus g of a. This is my value of a, and we'll use that one later on. So I will say for now it is a star. Now this is defined as g of b minus g of a is non-zero. Okay. So now as g of b is not equal to g of a, therefore c is definite real number. So it is exists and it is a real number. Now what about this function phi? Since this f and g, both of them are continuous over the closed interval AB, and we know that the sum of two continuous functions is also continuous. So this function phi is continuous on closed interval AB. So that we can write as f and g are continuous on closed interval AB, phi is also continuous on closed interval AB, and as f and g are differentiable on closed interval AB, phi is also differentiable on open interval AB, and phi of a is equal to phi of b already we have, because we have determined the value of capital A if this condition is satisfied. Therefore what we can say, a function phi satisfies all the conditions of Rolle's theorem. Therefore there exists at least one c in the interval AB such that phi dash of c is equal to 0. But what is the function phi? The function phi is fx plus a gx. The derivative of this function will be f dash of c plus a g dash of c equal to 0. So that will gives me f dash of c upon g dash of c is equal to minus a. But we have already obtained the value of a, that is minus of f of b minus f of a upon g of b minus g of a. So that will gives me the objective of our Cauchy's theorem, which tells you that there exists at least one c such that it will satisfy this condition, and which completes the proof of the Cauchy's mean value theorem. Let us have some alternating form of Cauchy's mean value theorem. In short, it is CMVT. So if two functions f and g are continuous on the interval a to a plus h, so instead of b I am just putting a plus h, and differentiable on open interval a to a plus h, and g dash of x is non-zero for every x is in between a to a plus h, then there exists at least one c, it is in between a to a plus h, such that f of a plus h minus f of a upon g of a plus h minus g of a is equal to f dash of a plus theta h upon z dash of a plus theta h. For now, instead of this c, actually this will be theta that I should write. Theta is in between 0 and 1. So there exists at least one theta. It is in between this, we have this. And how we got this one? Because we have a c which is in between a to a plus h previously. So if I subtract now a from this, that will give me 0 less than c minus a less than h. If I divide h, that will give me c minus a upon h is less than 1. So if I take this as theta, so instead of c, you can have now c minus a upon h is equal to theta, and theta is between 0 and 1. So the value of c you will have it is a plus theta h. So that's why we have a plus theta h here instead of c. And instead of c here, we have just taken theta is in between 0 and 1. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye.